Hi everyone and welcome to the channel. Today I'll be going through requirement 4 of Euclid's Elements. So let's get into our mind map. So, requirement 4. The fourth requirement requires the previous three. As we've said, they're all interrelated perfectly. And it states that all right angles are equal. But quite a few definitions are needed before we can establish the fourth requirement, which states that all right angles are equal. So before I go on, I just want to make a small note to illustrate what we've been talking about in all this series up to now. So in this mainstream video, as I said, from Numberphile, the presenter states that things start to get slippery with axiom 4, and again it's simply stated arbitrarily, like it doesn't even belong there, like it's self-explanatory, and yet again, or Norman Wildberger's video, he simply states that the 4 axiom basically means that you can just transfer one angle on top of another, and if it's a right angle they will always coincide. This is a very shallow view, and yet again no context has been given, no thought has been given as to why the fourth requirement is what it is, and we'll show how more deep and complicated everything is and how it's so necessary to go there. But we just need to add a few things. So this GeoGebra applet was initially meant for the summary, but I'll just use it a bit here and then I'll also add it again in the summary. So the definition in ancient Greek of Euclid's fourth requirement is "και πάσας τας όρθος γωνίας ίσας άλληλες είναι." And that just states that any right angle is equal to any other right angle. But a precise definition that we will give is a right angle is that ratio of a circle's arc to its radius that is formed by partitioning of a circle's circumference into equal parts using only a diameter and its perpendicular. Any such angle is called a right angle, which is equal to any other right angle formed in the same way. And we have a diagram here that will help us illustrate the point. So I'll get back to the mind map, and then I'm going to come back to this dynamic shape diagram. So for starters, we need to define angle, which is easy but not straightforward as you might imagine. So first we have to define, as we said here, we need a few definitions before we move on. So first we need to define symmetry. So symmetry is the attribute of being made up of exactly the same paths, comprised of motion from one location to another. This is also again apparent if we think in terms of constructions and using a compass and a straight edge. But use your mind for now, because it's the same thing as we've said anyway. So an arc is any part of a circle's path. How do we know that a circle's paths from one end to a diameter and from one end of a diameter to another are the same? So we know that the arc's semicircle circumference paths formed on either side of a circle's diameter are equal because either can be generated by the same radius. Define an angle primitively. We can define an angle primitively as the ratio of a given arc of a circle to its radius, i.e. angle equals arc over radius. Later we can define angles as number, i.e. angle equals arc length by radius length. So to our shape here, so let's go from the beginning. Imagine there's no shape here. So we start with a point, we define another point, and the shortest path, the unique shortest path between these 2 points is the straight line. we can extend this straight line undiminished as we showed previously. By this radius we can define this circle, and by the extension, as we said, we can define the diameter. Okay, so imagine we define this radius here, and from the definition of a semicircle that we just said, we use our compass or our mind, it's the same, to draw this path that starts from one end of the diameter and meets the same end of the diameter. Okay, so how do we know there's symmetry? Well, the exact same definition is used to do the other half. So if we were to use the definition, we could define it up to here, but at the same time the same definition applies, think of motion, if we went this way. So the circle is always this perfectly symmetric shape. That can't change. So we have now already established that the circle's diameter partitions the circle path, known as circumference, into symmetrical parts, known as semicircle arcs. So we know that the center partitions the diameter into equal radii, since any radius which is extended has the same circle point in common. The same center point, in common. The radius from the center point of a diameter which partitions a semicircle arc into symmetrical path is called a perpendicular. So it's this line here, perpendicular to that diameter. If such a perpendicular is extended, it will also partition the other semicircle into symmetrical paths, so that the arcs created by a perpendicular to a diameter are equal. And yes, we know this because the same radius forming the arcs on either end will coincide at the radius perpendicular which passes through the center. So now we're ready to define any right angle as the ratio of an arc formed by partitioning a circle circumference into equal parts using only a diameter and its perpendicular. And observe that no concept of measure or number has been used at all. Once we establish number, we can count the right angles in a circle. So much in depth to derive the 4 requirements, and we only have one more to go. And I just want to note here that visual aid from digital tools like GeoGebra, which I'm using now, and actually using a compass and straight edge really does help for all these ideas to sink in. But I want to make a note, as usual, that these visuals illustrate that these well-formed concepts hold, but we don't rely on these visual proofs. So back to the shape to show how nicely all these right angles are always equal. So if we move this shape in any way, shape or form, if we extend these lines, this diagram always holds symmetry, and these angles always hold symmetry. So to say that all right angles, to summarize, to say that all right angles are equal, we have to define what an angle is and derive that principle and understand symmetry and arcs and understand how important it is to define a perpendicular based on the fact that the perpendicular splits the diameter into 2 equal radii. So that's it for now, and in the next video we're going to go onto requirement 5. That's it. Thanks, bye.